Okay, I think we can get started, and our friends who join along the way, we'll let them in. So, as we usually say here, welcome back or welcome to the Mind and Life Europe MLE Friends series, Mind and Life Europe. We are really glad to see some familiar faces here, and we know that there will be many more of you watching down the road on our YouTube channel. So, welcome as well to those. As you know, this particular series was developed to showcase some of the latest and most cutting edge research and thinking from members of our research community, both our MLE Friends, our MLE Association, but also the extended research community, and to really share it with the MLE Friends subscribers and association members to develop in-depth discussions around some of these ideas. And so it's a platform where we go deep, and the discussion is usually quite lively and intricate. So this evening, I'm really happy to welcome Dr. Fernando Rosas, who is a two-time Esri faculty member. And so we were able to learn a little bit about his work on complexity science, complex system science, and emergence in the last two Esris. But because of the format of the talks at our Summer Research Institute, we were really only able to scratch the surface. And so we're really excited to have you back, Fernando, to walk us through more of the intricacies of your research and what you've been really trying to develop in the various fields you've contributed to in the last few years. So thank you so much. And I would like to introduce you as well for those who don't know your background and your current position. So Dr. Fernando Rosas works as lecturer at the University of Sussex and as honorary research fellow at Imperial College London and the University of Oxford. Previously, Fernando worked as a postdoctoral researcher at KU Leuven and the National Taiwan University. Fernando has a BA degree in music composition and minor degree in philosophy, a BSc degree in mathematics, an MS and PhD degrees in engineering sciences from the Pontificia Universidad Católica de Chile, and a lifelong interest in meditation and martial arts. His work includes significant contributions in mathematics, engineering, physics, and neuroscience. And I seem to recall that Fernando is also the author of an unbelievable number of scientific articles, something over 100 or 150. So I just want to mention that he's widely published and has really contributed a great deal to these different fields and also between these fields. And as I mentioned, he's also a former faculty member of the European Summer Research Institute. And so many of you might know him from this context as well. So with no further ado, I will leave the floor to you, Fernando, to offer your presentation, and then we'll have about 20 or 30 minutes at the end for questions and dialogue with the live Zoom audience. So please save your questions for the end, but we'll definitely have time for them. So just note them down along the way. So thank you, Fernando, and the floor is yours.
Thank you, Johanna. Very excited to be here and be talking about my favorite subject, that is emergence. So let me share my slides. This looks all right. Good. So yeah, the plan for today is to talk about emergence and how can we think about this scientifically. So just to warm up a little bit, I will show you some videos this is a beautiful video about starlings. And the idea is that when we see something like this, we feel something special is happening. You know, there's something here going on. We feel that this flock of birds is doing something unique. But it's very hard to put the finger, like what is that thing that is so unique about it? And that's part of what this work is about, like trying to really try to understand why is this special? Why is this different from many other things? And part of the attractiveness of this, I think, is that the possibility that this is actually a superorganism. right? So this is actually a real photo. This is not AI. This is a flock of birds that look like a meta bird, right? So is that true? How could that be? And some people, when they speak about emergence or flocking and all of that, they say, "Oh, it's this way of talking, it's this way of describing things." But this video, I find it very amusing to the degree that it really shows that this is not just a way of talking. This is something that makes a difference. So the fact that these animals are working together is not just a way of talking of me as an observer of what is happening, but because they work together as one unit, they are achieving effects in the world that they couldn't achieve on their own. So and we have all type of experiences, direct experiences of this, right? When you go to see an orchestra, it's very different to hear everyone separately than the whole orchestra working as a unit, right? So what is this? How can this happen? And what does it mean? And what is it good for? So that this is sort of thing that we would like to think about. And the plan for the presentation tonight or today, depending on your time zone, is first to argue why do mathematics about this? Because there's a lot of works on philosophy and other disciplines about emergence, but in this particular case, I'm interested in mathematics. So I will start arguing why that makes sense. Then part of my proposition would be to think of emergence not as one thing, but actually as multiple things. And in order to illustrate that point, sections 2 and 3 will propose a different way to think of emergence that I think both are right, but both are different from each other. So it's a bit of a taster of how this sort of pluralistic view of emergence could look like. And at the end, I will wrap up and talk a little bit about human consciousness, because why not? So, before talking about emergence, let's talk a little bit about philosophy and metaphysics and things like that. So, for example, one possibility is to take a very reductionist stance where we would say things like, well, if you see a duck is a machine made of pieces, and the brain is another machine. And everything is just a machine. The only question is how many pieces do you have and how small they are. So human brains are special just because they have a lot of pieces and the pieces are very small. That's it. And that's sort of a very strong reductionist approach. We say there's nothing to see, keep walking. It's just a number of magnitude. Now, reductionism as a method, I think we can only love it. Like there's no reason to reject this. For example, if you want to achieve something hard, like I want to climb this mountain, how would you do it? And the way we face this type of situation is spontaneously. We divide the problem into separate chunks. Then we solve each chunk separately. So how do I arrive to the base camp? How do I get to the second camp? And each of these sub-problems, we solve them separately. And after we have the single solutions, we connect them together, and then you have so many great things that we have achieved with this approach. So for example, the periodic table, we know that all molecules are based on the same little things, and we got there because we divide the story and understood how the parts relate. So this is extremely successful. Now, the problem is that this is a strategy and has limits. So for example, what happens if the very thing you want to study, as soon as you divide it into sub-pieces, it disappears, right? So for example, maybe we want to understand a human in its integrity, not the organs or the subsystems. Or what if we want to study music and we cannot really separate the musicians, because as long as the musicians are separated, the whole orchestra disappears, or an ecosystem. So in many cases, the very interaction is the thing we care about. And then it doesn't make so much sense. Sometimes the gap between the parts and the whole is so large that by explaining the parts, you learn basically nothing about what you care about. Another consequence is that by taking this very strong reductionist view, we tend to get into this mindset that I call, like joking a little bit, microscopic chauvinism, in the sense that we start thinking that small things are more real than big things. And I truly think there is no reason to believe that. But that's something that you naturally start thinking, oh, brains are more real than emotions or thoughts, because brains are made of these tiny pieces that I can touch, and these other things are a bit weird. So we get to these cognitive biases. And one problem of that is that we start thinking that big things are epiphenomenon, like ourselves. We are an epiphenomenon of all these particles that are obeying physical laws. And I don't think that's great, to the point that very smart people like Steve Weinberg, a Nobel Prize winner in physics, he said, the more comprehensible the universe becomes, the more pointless it seems. So as soon as I see someone smart saying something like this, I feel that we did some wrong turn at some point. And where was that? And I think the wrong turn we did at some point is that we start confusing reductionism from a method to reality. And it's very different to think reductionism is a way of going about things, and it's very useful sometimes, sometimes it's not, versus to saying, I think reductionism is true. This is the way things work. And so I think, and a lot of people identify reductionism with science. So what science do is to split things and study things and then connect. I don't think that's true, actually. I think science is about explanations. It's about predicting what will happen after, especially after we intervene. Like, if I do this, what will happen? If I do this surgery, what will happen? Treatments, etc. And reproducibility. Like, if I do this and this happens, can I trust that it will happen again if I do it again in a different country or something like that? So these are things that science is about. And reductionism is a way to get these things. So I don't think any scientist is intrinsically interested in reductionism. We are interested in reductionism to the degree that we get these other things that are the things that we care about. And once you see things from this perspective, I think, at least for me, it's easier to think of reductionism as a method to get the things that we care about versus a philosophical position of how we think the world works. And if we assume reduction is a method, maybe there are other methods, right? So what could be other methods to do science? Can we do science that achieves to the same aims but without reductionism? And to think about that is where emergentism comes as an alternative. So what is emergentism? One way to think about this is to say, to believe that there are some things that cannot be explained from physics. So for example, let's say we have a perfect theory of the small components of the universe, like particle physics or something like that. Do we believe that from that theory we should be able to predict social phenomena such as communism? Most people would say no. Some physicists would say yes, but most normal people would say no, it's not possible to derive communism from physics. So that's not a controversial statement. The controversial statement is, why is that not possible? And there are two options basically to answer that question. One is to say it's impossible in principle, so it just cannot be done. Why? Because macroscopic features, big things, have irreducible causal power. So there are things that big things can do that cannot be explained in terms of the things that small things can do. This is one position that is a bit too strong to most scientists. And for that reason, a second position was invented that is called weak emergence, where the idea is that the macro, the big things, can always be reduced from the small things. It's just that often it's very hard, or perhaps in practice impossible. So it's not possible to go from physics to social phenomena, but not in principle, just in practice. Why? Because the computation is too hard. We don't have enough resources or time to do the calculations, but in principle, it could be done. So this is sort of a middle ground that many people like because it feels like a nice compromise. Now, my position here is that I see this discussion between some views of emergence that is going a bit too much, in the sense that you say emergence is what you cannot explain. And as soon as you explain it, it's not emergent. That to me sounds like a dead end. It's like, okay, I cannot get anything out of this, so I'm not interested in that extreme. Now, in that extreme is saying emergence is nothing really, it's this illusion. It's just this way of talking, and I'm also not interested in that because, like, what's the point? So my interest is in between. Like, what type of positions we can take in between these two extremes, which I feel both of them are not very helpful. So what can we do here? What type of positions we can take, and how much do we have to pay, and how much we can get out of it, and stuff like that. And more concretely, the goal of my research has been to build some philosophically lightweight framework in order to reason about emergence, so that one, we can formally establish hypotheses of what do we mean with emergence, because one problem is that it would be nice to be clear, like by emergence we mean exactly this. And hopefully, if we can be precise enough on how we frame our questions, we could be able to arrive to ways to verify those questions from data. So let's say I say consciousness is an emergent property of the brain activity. What do I mean by that? And then can I formalize my statement such that then I can do an experiment in the lab, I can collect data, and then I can validate that hypothesis with statistics. So experimental science. So that's the hope. And my interest, like if consciousness is an emergent property of the brain, I would not like to convince people by the virtue of how I move my hands with a lot of eloquency. I would like to build to let that conclusion to arise from an experiment. So the only thing that you do is to postulate the hypothesis, and then you let nature to tell you if that hypothesis was in the right direction or not. So to connect a bit emergence with empirical science, that's the goal. Now, philosophy has been dealing about emergence for very long, and mathematics and science from much less time. And I'm not here to say we should stop doing philosophy and we should change it for mathematics. Not at all. I feel that these two things are different and complementary. So I actually feel that math can help and contribute something to this discussion that is ongoing. How can it help specifically? First, it can guide the intuition in complicated domains. So for example, there's this case in mathematics where people start thinking about infinities, and some infinities were larger than other infinities. And then you start like, how can I reason about that? And it's actually very hard because it's not intuitive. But then mathematics can help you, can handhold you in these domains that are a bit counterintuitive, and then you can arrive to conclusions that people can agree with. So for those things, mathematics is very good, and emergence is one thing that is very counterintuitive, almost by definition. So I think math can help for that. Second, mathematics is very good to be precise. And by using mathematical tools, we can try to be very precise in what we mean by emergence. And also math can be connected with statistics. So if we do those formalizations in the right way, we might automatically get tools that then we can do experimentally on data. So those are, I think, the three main things that we can win by bringing math into the discussion. Now, I think there is an interesting relationship that mathematics and this sort of engineering approach to emergence is not really asking what emergence is directly. It's more like, how can we use it? How can we measure it? If we measure it, can we do something with that number that we get? And philosophy is more like, what is the nature of emergence? And I strongly believe that there is a potential virtuous circle between these two questions. So you ask what it is, then how can I use it? And by using it, my experience is that we learn a little bit on what it is. So by using it, we learn a bit more on what it is, and by thinking again what it is, we use it in a different way, and then and this circle starts looping and looping until we do progress. So that's the way I really think there is the ideal situation is to have a dialogue between the philosophical views and the more math/engineering views, such that all can contribute to this discussion and we can work out this together. So that's the motivation. Now, let me present you one way to make mathematics of emergence. And this way, I will call it mereological emergence. This is a sort of a fancy word to say made of pieces, made of parts. So in this view, we're going to focus in systems that are made of parts. So for example, a flock of birds is made of birds. A group of humans is made of humans. So that type of thing. And the informal definition is that we're going to say a whole, a collection of things is emergent, has emergent properties. The whole is emergent if it has properties that cannot be traced to the properties of the parts. That's the informal definition, and from here we're going to build up into something more formal. And to do that, I will take inspiration in this old paper from these three gentlemen about the brain. And they were thinking, what does make the brain? So the brain is a physical system that follows physical laws, but it's special, the human brain. It seems that it's distinct from, random physical objects like rocks rolling down the hill. What does it make it different? And they propose that the brain has two properties that are distinct. One is that it's differentiated, so it has different parts that do different things. So we have a visual cortex that coordinate vision. There is, the motor cortex that do actions, and there is some parts about self-reflection, etc., etc. So we have different parts of the brain in charge of different functions. Now, what is interesting is that these parts are not just differentiated, but they're also integrated. So at the same time, they work together as an orchestra in a unified way. And what is really interesting, I think, is that intuitively we will think there is a trade-off between these things. So you have to balance yourself. If you are too differentiated, no, that's not integrated, so you have to push a bit more to integration. What they show is that actually you can have your cake and eat it, which is very counterintuitive. Like, how on earth could you have these two things at the same time? And this is my favorite visual representation of what they mean in my interpretation. That means these are three rings, and with your imagination, if you take the blue ring out of the picture, you will notice that the red and the green are not connected if the blue is not there. Now, if we take the green out of the picture, the red and the blue are not connected, and etc. So this is a triple connection where is entangled. If I try to disentangle the three things, I cannot do it. But as soon as I take one of them out, the other two are not connected. So this is a triple connection that cannot be explained as a sum of pairwise connections. And this is something not reducible, right? So this is the type of construction that I think can explain this thing, because they are integrated, they are not dissociated, but at the same time, locally, they are differentiated because two of them are not connected. Only the three of them are connected. And in that sense, I think you can have differentiation and integration at the same time, having it at different scales. Now, how can we make that notion? That's what I will call synergy, when you have these two things at the same time. Now, how can we make this operational? How can we measure this? And for this, let me walk you through a cartoon. The idea here, we have, you live in a house with other people and you want to eat your favorite cookies. You want to get your cookies and you find that somebody stole them. So you get very angry, and as a rational person, you hire a detective to find who stole your cookies. And there are 9 culprits. And the detective will ask 2 witnesses who took the cookies. So the first witness will say, yeah, I saw that the culprit was wearing a mustache. And with that, you're ruling out 5 out of 4. So you're doing good progress. And they will say, yes, and he was wearing a hat. So by the information given by the first witness, the detective is uncertain between two persons. Now the second witness come in and say, yes, mustache, and it was a red hair. And by combining these 2 informations, we can find who the culprit was, right? Now, what is interesting is that the information given by these 2 witnesses is of different kind. Mustache is redundant. Mustache is something that the first and the second gave, so is in both places. This hat and the red hair is unique because it was given by one and not by the other. And the identity of the culprit is something synergistic because it was given by both, but it was not given by neither of them separately. And this is the idea of synergistic information. So you can have 2 sources of information, and from both you can learn something that you couldn't learn from one or from the other, but you can get it from both. And this is a common phenomenon in information. And from here, there is a whole way to measure this that I will not bother you with, but trust me, there is a way to quantify this synergistic information. Now, let me show you how you can use this. We study Bach, the music of Bach, using synergistic information. And the intuition was, if something is synergistic in the universe, that should be Bach, right? And here, these are songs, these are chorales, that there are 4 voices singing at the same time. And as you can see visually, they're doing different things, but they're also sort of integrated. So in a way, the inspiration was maybe this is working like a brain a little bit. And what we found, we have here a way of measuring synergy. So this quantity is a quantity that whenever it's negative is synergy, whenever it's positive is non-synergy, is redundancy, the opposite. And what we saw, we compared the music of Bach against the music of Corelli, who is a contemporary, and we saw this very, very distinct property. And then we tried to understand why is that? And by doing extra analysis, we realized, so the music of Bach is sung by 4 people. All the connections are blue, so everything is synergistic. And that means if I know what the bass is singing, I have no idea what anyone else is singing. If I know what the bass, the tenor, and the alto is singing, I am almost sure what the soprano is singing. So the whole thing is constrained, but locally they are unconstrained. By knowing what the bass, I have no idea what the alto is singing. They are uncorrelated. It's a bit like the rings. The Corelli is not like that. In Corelli, if I know what the viola is singing, I know what the cello is playing because they are very, very strongly coupled. And that is because they are basically playing the bass line, both of them. And in that is super non-synergistic because there are very strong coupling between these 2. And the conclusion out of this model study is that synergy is this thing that allows local autonomy to coexist with global cohesion. There's 2 things that seem opposite. So you can be autonomous from your neighbors, but at the same time, you can be connected with the whole thing. And that's what synergy gives you. So now that we are expert in synergy, the idea is to use the notion of synergy to study emergence. And how will this look like? The idea here, we have some description of a flock, for example. So we have a vector where the components of the vector are the positions of birds. This flock is evolving in time, so the flock is moving in some way. We arrive to a second time point. And at every time point, we can measure a collective property that in case of flocks, we are going to measure the center of mass, that is the center point of the flock. And what we want to study is how the flock move, bird by bird, and also how the center of mass moves around. And intuitively, we're going to talk about two types of emergence. One is downward causation, that is when the center of mass in the past affects what specific birds are going to do in the future. Downward in the sense that the whole is constraining what individuals are going to do next. And causal decoupling, that is when the center of mass affects the center of mass in a way that is not explained on what the birds are doing. And let me give you a bit more concrete example. So here we have artificial birds. This is simulations, but it's useful to fix ideas. So here we have a very rigid bird flock in the left, where they're so rigidly connected, they're just spinning in circles. In the other part is completely unconnected birds, so they're doing whatever they want. And the red dot you can see is the center of mass. So in one case, the center of mass is fixed, in the other is doing whatever because birds are ignoring each other, basically. In the center, we have something in between. So there is relative independency between birds, but the center of mass is doing something a bit more consistent. And by doing some measurements, we can conclude that there is emergence in the middle. And what do we mean with this? What we're doing is the following. We ask the birds, bird number one, where is the flock going? In the first case, every bird knows where the flock is going. So there is nothing surprising. Every bird can know where the flock is going. In the crazy bird example, nobody knows where it's going because nobody knows anything. But the flock also doesn't know where it's going. In the military bird case, the flock knows where it's going, but everybody knows where it's going, so it's nothing surprising. In the other extreme, nobody knows anything, so it's also nothing surprising. In the middle, there is this interesting case where the birds don't know where the flock is going because they are relatively free to do whatever they want, but the flock knows where it's going. The flock can predict itself because the movement is relatively consistent. So it has a notion, oh, I'm going in this direction. So the flock has a consistency that can predict itself, but none of the birds can tell you where the flock is going. And this is what emergence means in this case. You have a collective property that has causal ability on itself, but that cannot be explained from the causal ability of the birds, of the components. And we have measured this on humans, in brains of humans. And this is an example. We measure fMRI data with some stuff that I will save you from the details. But the idea, we measure the capacity for emergence from healthy brains and from brains of patients that had some type of brain problem. So they are in vegetative state or semi-vegetative state. And what we see is that the capacity for emergence drops from normal controls to minimally conscious to vegetative patients. So this is an indication that the types of dynamics that healthy brain have seem to be compatible with supporting this type of emergent properties that as described before. And this drops as brain conditions make people lose consciousness. This is not proving anything. This is an indirect evidence supporting that there is an interesting connection. And we have more results of different kinds, but I will save you the details. So So this is one way to think of emergence. And I hope the idea is roughly clear. There is a lot of mathematics and more details, but I wanted to provide a sort of a high-level idea. So the whole point is about parts that are doing specific things so that there are collective properties that have ability on their own, such that the parts cannot explain what is happening. Let me now walk you through a different way to think about emergence, and which we will call a hierarchical emergence. So this comes from an intuition that we all have that the world is stratified. So we have the genomes, and then you have cells, and you have communities, and then you have organisms, and then you have ecosystems, and all of this made of molecules that are made of atoms, that are made of quarks, that are made of superstrings. And so you have all these sort of scales of reality, and each of them seem to have their own rules. So the social rules are different from the cellular rules, that are different from the molecular rules, that are different from the subatomic rules. So it's sort of interesting that every scale of the world seems to have their own rules. Now there is a sort of a parallel question about abstractions. For example, we have this gentleman there looking at this sphere made of bronze and thinking, oh, this is a sphere and it's made of bronze. And it seems that there is something about scales here also, like you have concrete things and then you have abstract things that are a bit more at a different level. And these were the questions that I was thinking about when trying to, is this related with emergence in some way? Another question related, I'm springing ideas and then I will try to connect them. The third ingredient to the soup is the brain a computer? So this is a question that people debate periodically, never arriving anywhere. So because the problem is, under some definitions, the brain is obviously a computer because the definition is so wide that anything is a computer. And on other definitions, the brain is obviously not a computer. But in neither definition, I learned anything about the brain. So I found very, very frustrating that discussion. And then me and colleagues, we start thinking, can we change the definition of what does it mean to be a computer in a way that we can learn something interesting? And the idea we had was to focus on what is the idea of software, what makes software special. And the thinking is the following. Here in front of me, I have a laptop. A laptop is a physical system. That means it follows the rules of physics, right? Now I can have a rock, I can put it in a hill and it can start rolling. And that is a physical system following the laws of physics. So the same as my laptop. However, I would say my laptop is a computer, it's computing and do interesting stuff. And I would not like to say the rock is a computer. What is the difference? What does make the laptop a computer and makes a rock a non-computer? So one proposition that we put in this paper is that computers have separation of scales. What do I mean with that? Whenever you write a code, like the one here, this is sort of a very simple code. You say A is equal to 2, B is equal to 3, C is equal to A plus B, print C, and you will see on your screen a 5, right? So that's the basic computer algorithm. Now, the interesting part is the following. If I run the script once, I will get a 5 in my screen. If I run it again, I will get a 5 in my screen. And if I run again, every time I run it, I will get a 5. However, every time I run the script, the physics underlying that algorithm are going to be entirely different. So my computer is made of trillions of electrons and particles, and every time I run the algorithm, they are going to be doing different things. However, the algorithm will be always the same. I will always get the 5 in my screen. And that's not a coincidence, that's how computers are made. And that's why computers are useful. Because they are a messy physical thing, but on top of this, there is this logic of the software that is very reliable. And somehow all the unreliability of the microphysics is averaged out in some way such that there is a higher scale, a coarse graining, that is completely reliable, and I can do programs and software and all the things that make computers useful. So, and here the perspective would be any system that has this separation of scales is a computer. And rocks don't have that, and that's why rocks are not computers. Now, let me convince you that toilets are computers. And the argument is the following. Whenever you go to a toilet and you flush it, the water goes out, and then the water will start coming in, and there is this floating device that is down, and the water comes in, and at some point the water will push the floating device up, and the floating device will close the entrance of the water, and the thing will stop. In computer science, that's called a while loop. So while the floating device is down, let the water come in. As soon as the water goes up, then cut the water influx. So that's an algorithm, I believe. And every time I flush the toilet, this algorithm is running on a physical substrate that is very messy. You will have turbulence in the dynamics of the water, like the details of the implementation of the algorithm will be incredibly complicated and never the same. However, every time I flush my toilet, the algorithm will work the same way. The same way we get the 5 in the computer, the toilet is doing the same thing. And that's why toilets are useful. If every time I flush the toilet, something random happens, I would not like to have a toilet in my bathroom, right? So the reliability of the toilet at that level is what makes toilet useful. And in that sense, I would argue the toilet has its own logic at the macro level, and in that way is a computer. Now, an interesting point is that, for example, if you have a self-driving car, The self-driving car has cameras and a little sensor, not too many, and with that, the self-driving car navigates around and navigates better or worse. But the self-driving car is not measuring every electron around their environment. They have a very simple, like rough description of the environment, which is never enough sufficient in order to navigate. And we are roughly the same thing. We are systems built on quantum mechanics, but we have no idea the quantum mechanics around us. Our sensors are very coarse-grained. Nevertheless, we survive and we do our life. So the world around us seems to be built in the same way. And because it has this property of separation of scale, we can survive. So this separation of scale seems to be very important. And the more you start thinking about it, you start seeing it everywhere. So how can we put this into mathematics? I will go very high level on how this works, but the core idea is you start from some construction called the epsilon machine. And here the idea is that you have some process, and that process can always be explained as a hidden process that is very simple, represented in the yellow bars. And this hidden process is simple, but I cannot observe it, and is emitting the data that I can observe. So the data that I can measure in a real process can be extremely complicated, but the argument is I can always explain these observations as coming from a simple process that I cannot see, and is generating where I can see. And this is a mathematical truth that you can always build a latent process that explains my data. And now the next twist on the story is that latent explanation can be framed as a dynamical process that is doing this and then doing this and moving around, or it can be framed as a computational process. It has this dual nature. You can show it as a computational process or as a dynamical process. And when you show it as a computational process, it looks like this. So these yellow things are states. So you are in a state, and then something happens, and then you move to another state, and then something happens, you move to another state, and then something happens, you move to another state. So you're basically explaining your data, whatever you're observing, in terms of this hidden machine with states that is jumping between states. That's all I'm saying so far. Now, if this is all math, and this is all true, to the degree that math is true. So you have to believe me that this can be built, this type of descriptions. Now, what is interesting is, what if I have now data at the microscopic level? Then I coarse-grain my data, I simplify it, so I have data at a middle level, and then I simplify even more and I get to a higher level. You can explain your data at the different levels, and this will result in machines that are more or less complicated. And an interesting question is how these machines that explain my data at different scales will relate to each other. And naively, you could think, of course, it should become simpler as I go up, because my data is simpler, so the explanation of the data should be simpler. But that is not true in general. Sometimes you can simplify your data in a way that you are sort of hiding important stuff, and then to explain the remaining part is a mess. So the machine that you have to use is much larger. So the machines between them across scales in principle are unrelated. But in very specific scenarios, you have this sort of matryoshka type of thing, where the machine that explains the micro level has a lot of states and is very complicated, and the machine that explains the level above is the same thing but simplified. So instead of having 12 small states, it has only 3, and instead of having a lot of small arrows, it has these big arrows. So you have these nested explanations. And so with that, we came with this idea of computational closure, which means you start from your microdata, X, that is a simpler, like your measurement process with all resolution. You build an explanation, that is E. Then you coarse-grain your data, and then you explain your coarse-grain data. And the question is, this theory, this explanation of the simple data can be explained as a simplification of the explanation of the complicated data. Can I get to the same point by the two roads? In one way, I have micro data, micro theory, I simplify my theory. In the other, I have micro data, I simplify my data, then I build a theory. Do I get to the same point? And whenever that works, then the scales are independent. So basically, this captures very mathematically the fact that in the computer, I run the thing and I get a 5 the whole time. because it means that the whole way that the macro works is self-contained. It contains everything that you need in order to explain everything. So it's sort of its own thing. So it's made of the small parts, but it's completely self-contained. Let me walk over this. Let me simplify all of this. Let's gloss the details. So just to take sort of a high-level perspective, this is a different view of emergence from the previous one. This is a bit more complicated. I would say to a large extent, this seems more complicated than the first one. The reason is because I have worked on it for less amount of time. And that's why I find it also a bit more difficult to explain. The other one I have been working for years, so I understand it very well and I can explain it very simply. But the thing I would like you to take home is this is a very different view of emergence. The first view of emergence is all about parts and how they come together. Here, there are no parts. We never talk about parts. It's all about scales. And here, in this view, there's a lot about autonomy. So I like the logic of my toilet not to depend on the small details of the turbulence of the liquid. So I want the macro level to be independent. In the other case, there is a little bit of that, but that's not the central point. In the other case, I want the birds not to predict what is happening in the top level. So it's similar, but it's different. In this case, for example, why this computational closure is interesting. For the system itself, it means that the system has levels of description that are self-contained, and because of that, they can be controlled at their own level very efficiently. So for example, myself, I think I have these levels, and I could try to control myself at the quantum level, but that would be a pain because it's very complicated. But I can control myself at the macroscopic level. That is what I do every day. That is very simple. And because of this closure, I can control myself efficiently without controlling the degrees of the freedom that are below. So you can control some part while forgetting the rest, and that works. And that is important because that's the way we survive. For a researcher, this is useful because you could study a system, and because you know these levels of description, you can go to a high level of compression and describe just that, and you know that that description is going to be complete. You're not making approximation errors because there exists this separation of scales. So this property has a very good consequences. So let me wrap up a little bit the whole story. So what is emergence? My claim is that emergence is a bit like intelligence or complexity. In the beginning, you think it's this one thing, like intelligence. People say, oh, intelligence is the thing. We have to find the factor of intelligence. And the more you try to find it, you don't find it because you start seeing these little flavors of it. And you try to reduce it, and they don't seem to reduce because they seem a bit distinct. In complexity science is the same. In the beginning, people thought complexity is this thing, the single thing. We just need to be smart to find the right measure of complexity. Today, nobody believes in that anymore. We all think that complexity has many facets, and depending on what you want to do, you study this facet or this facet. So I think the same with emergence is starting to happen. This is my sort of approach to the problem. I think emergence shouldn't be tried to be collapsed into a single thing. It has all these different flavors, different facets. And we are in the process of building formalisms that capture specific facets and not the other one. And by learning how many facets makes sense to distinguish how they are related, then we make progress in understand what emergence is. What are these different flavors? Here I presented two. One is to think emergence as computational closure. And here the idea is that there is a decoupling and relative autonomy between the scales of a system. So the system, like the computer, has the software level that is relatively autonomous with respect to how it's made, how the smaller parts are. This is the second flavor I talked. The first flavor is this emergence as whole more than the parts. And here the whole point is about when collectives made of parts have properties that the parts don't have. And it's sort of tricky because you can see that sort of they're talking about the same thing, but at the same time, the emphases are very different. So for example, in the computational closure, you don't need even to define parts. Parts don't enter into the story. The second is all about the parts. It's all about what the parts can do and what they cannot do. And I would not like you to think, I believe those are the two flavors of emergence. I think there are many, and we're in the process of discovering them. And these are two that I have worked and I understand well, and that's why I'm presenting them. But there is a bunch of other ones already developed and more hopefully to come. And I think what we should aim for is to have a constellation of different types and then try to organize how are they related. Now, what unifies these flavors? Because it's not that anything is emergent. Like there are specific things they have in common. I think one thing they have in common is this emphasis on the different scales of a system. And here, one of my favorite sort of word-related facts is that matter and pattern, the words come from mother and father etymologically, which is very beautiful, right? And I really think that matter, when you have a piece of matter and you zoom in and you start expanding the scale and see the details, it suddenly disappears and becomes pattern. Or similarly, you have a pattern, you zoom out and it looks like matter. So I think pattern and matter are the same thing, but depends on if you're looking at it from above or from below. And it's all a matter of scales. So I think Emergence is trying to get into how scales work. And there are different questions. For example, are scales separated? And then you have computational closure. Or are interactions across scales? That's an interesting point. Like downward causation is something you cannot study with computational closure because computational closure is all about separation. But sometimes you want to understand if the flock is affecting single birds. That's something you cannot do with the second framework, you can only do with the first. So now, what about consciousness? And let me just throw some ideas about this and we can expand more after if people are interested. So, and this is from, I took this 5 minutes ago just to talk about this. This is on the question of, can AI be conscious? And one interesting way to think about this problem is that systems have many scales, as we have been describing, and you could reframe the question instead of saying, is AI conscious or not? What type of identity you need to have between a human and an AI so that you can attribute consciousness to the AI? So for example, the bottom level is microphysical description. And I think most people will agree that if the microphysical description between an AI system and a human would be like completely the same, we would have to accept that AIs can be conscious, because you're saying like everything is exactly the same. I think this is relatively uncontroversial. Of course, you could say this will never happen. This is more of a thought experiment. Like if we identify everything, then we have to accept it. But the interesting question is, what can we push this higher? So can we accept AIs and humans not being built exactly in the same way, but in the sufficiently similar way so that we can think that AIs are conscious because humans are conscious? And so if we take this step, this is sufficient and everything above is necessary. Now we could take another approach. For example, we can, this idea of computational functionalism. Like, I don't care how humans are made. I care about how human neural patterns work, like what type of neural activity we have. So it's a functional description. And then one different argument would be to say, well, if the functional description of AI is the same, equivalent to a human, if the type of activation patterns inside of AI are functionally the same, equivalent to a human, then maybe we would need to accept that. And if you say that is true, then you can accept differences at the microphysical level, and you would say that doesn't matter because the functional level has to be the same. And then the input-output behavior would be necessary but not sufficient. Another approach would be to say, no, function alone is not enough. That's too superficial. I need causal architecture. I need the code. It's not only that they do the right thing, they have to do it for the right reasons, because the causality between neurons is the same. And that's another position that one can take. And then you would say, being microphysically equal is not necessary. It's sufficient, but not necessary. But the necessary thing is causality. And that could be another position to take. Another position that some people take is about life, which is a bit more than the causal structure and is much more than just function. And in that case, you could say, if you take the life structure of a human and you can reproduce that in silico, then that would be enough to accept that consciousness, that the AI can be conscious. So, and my take would be, I don't know which of these things are true. And I think nobody knows. But having this map in your brain helps you to take a stance yourself. So what I like of this approach is that this is not giving you fish, it's giving you a fishing rod. So you can make your own opinion by thinking, what do you think is the right level? My and there are different theories outside, and they are going to think this is a different level. Like there are some theories of neuroscience that think functional is enough. Some theories think causal is enough. Some theories say the full causal embodied life is enough. So there are different people thinking different things, and I think each of us we have to make our own mind because nobody knows. This is my personal take. So and which has been changing over time. But this is sort of my credences. As you see, I'm not completely sure. It's a bit distributed. I'm pretty sure that having input outputs indistinguishable, like basically, GPT is achieving that already. I don't think it's enough at all. I also don't think that having the functional level the same is enough. And some years ago, I was much more convinced about the function, but now I really think it's not enough. My current guess is about the causal architecture. So even if the thing does everything externally and internally the same, that would not be enough. It has to be built in the right way. Every day I like more and more this idea that maybe the structure of life is necessary, but I'm still not super sure about it. I'm thinking about it. Maybe in some years I would switch this too, but for now this is what I believe. And I also am not very sure that the actual microphysical description is necessary. So maybe that can be different if we ensure some other level to be true. So this is my personal take on the question. Now, as I said before, I think that what is more useful at this point in time is for people to make their own beliefs on this. Try to be informed, but it's good to see the options and then make responsible guesses. And yeah, so let me one last thing before finishing. So is emergent answer? And I think we don't know. So this is all very recent work, and there is a lot to be done. So it's exciting times because I feel we're making progress and we are starting to use emergence for different things. But if it's going to be the answer of conscience or anything else, only time will tell. And with that, let me thank my very synergistic collaborators. So this is the work of a whole team of people working on this for many years. And thank you for your attention.
Wow. Well, thank you. Thank you, Fernando. Yes, applause from all of us. I think if we were in the same room together, you'd be hearing our applause. What a fascinating really exploration of the terrain, which is emergent itself. And thank you for also offering this generously pluralistic view of what's been developed out there, and to really invite people to think critically about these different modes, I guess one could say, of understanding. So I am imagining that there are a lot of questions, maybe some comments from other researchers in the room. So please feel welcome to raise your hand. It'd be helpful if you can raise your virtual hand so we can see you at the front of the room. But if you can't unmute yourself, that's fine. You can pop your question in the chat and then we can read it out. But please feel free if you have questions, and please don't be shy also if your question is just very general and you feel that it's an introductory question. That's also an important part of the discussion here. So please feel free. Yeah, Marika.
Hello, great talk. Thanks a lot. And I was wondering, so you talked about identifying emergence, but of course, emergence also arises in some way, like sometimes maybe things emerge from other things. Do you have any idea about how does it, so almost the dynamics of like what is the force that makes something emerge from the before it's there?
Yeah, that's a great question. Let me first clarify that there is an informal way of talking about emergence that is good not to mix. So not everything that emerges is emergent. There is a way to confuse emergence with self-organization, I would say, because self-organization is something that happens spontaneously. It's like you have some primordial soup and eventually, bloop, some structure self-organize spontaneously. And I would not put that into the same story because although the word that we use to describe that, this is emerging, it's more like buoyancy, it's like something is coming out to the surface, but I would not say it's the same as the same sort of thing about scales and all of that. So that is the first clarification. Now, second point, closer to your question, everything that I show is very behavioral in the sense of is based on patterns that I observe and I do statistics and I claim stuff, but it's not much about mechanisms. And the natural question then is, okay, what are the mechanisms that make this happen? And if I would want this to happen, how can I make it happen? Or if I would like to predict before anything happening, how can I predict if this is going to happen or not? This is an area of active research. We know personally, I know much more about the conditions for the second type of emergence than the first. I'm just finishing a paper that I think I will put to the archive this weekend on emergence and symmetry. So, and the main result is whenever you have symmetry in your system, you have emergence of the second time. Then, if there is something symmetric, there is a way to factor that symmetry out, and that will give you a simpler description of the system that is self-contained. And then there is a lot of consequences out of that. But so I think a mechanism for the second type of emergency is symmetry. I don't know if that's a mechanism, but it's a way to achieve it. Like if you have a system that has symmetries, then you will have these scales. For the first type of emergence, I know very little actually. We know, yeah, we know some corner cases of how to create it, but not so much. And that's part of the work we're hoping to do.
Thanks, Marika. Bruce, your hand is up. Want to unmute yourself? No, you were unmuted just a moment ago, and now you're muted.
Right. You can hear me now.
Yeah, great.
Good. Well, thank you very much for a very interesting discussion. I have a very basic question. Have you considered the assumptions on which your entire field of research is based? And I may make one or two suggestions of areas that you might like to comment on. You said at one stage that mathematics is true, whereas I think it's generally agreed now that mathematics is the language which is used to conceptualize lived experience. You seem to have excluded lived experience in the form of the observer in everything that you've said, and the third area where you have essentially compared the brain to a working machine, and I noted with interest that one of your collaborators was Arnold Seth, who is a strong proponent of predictive processing, which is essentially a machine-like system, which certainly encourages behavior based on previous experience, but does not explain things like creativity, which appears to come out from left field, if you like, as far as predictive processing goes. So those will be just three areas, and also the assumption that consciousness emerges from the brain rather than that consciousness is primary and cannot be taken out of the system because everything that the observer, the researcher, is looking at is done from the experience of the observer's lived experience. We cannot take lived experience out of it. All we can do is conceptualize using various languages, including science and mathematics. So just a number of points. Have you considered all those assumptions to your research?
Thank you. I completely agree with all the points made. Let me see if I remember all of them. The first was the role of the observer. I completely agree. I think I said in the beginning that the theory is mainly on data more than things on their own. So there is an observer implicitly because you're always studying the data that you're getting. That is always the data that one is like a perspective, right? And sometimes the conclusion is going to change if you change the perspective. Although I completely agree that in the whole presentation I didn't put an emphasis that there was always a perspective there. And to some degree we have chosen to fix it for now to make the problem a little bit more tractable, but there's definitely interest in saying, okay, what happens now if I change the perspective, how the conclusion will change. So that's one part. Now about the computer and the brain, I hope I didn't uh, said something I don't agree with, but I hope I never said that I think the brain is a computer. I just said this is one way to formalize what the distinction between hardware and software is, and is one way that you can apply to study the brain. I don't think the brain satisfies that condition. For the reason that I don't think the brain has a software in strictly speaking. Maybe some parts of the brain to some degree in their activity has some properties like this, but I'm I would be very surprised if the brain as a whole has the software in the way that this theory works. And actually, you mentioned Anil Seth. So Anil likes predictive processing, but also Anil is very strong against the computational functionalism. So he don't believe that the brain is a computer, and he don't believe there is a separation of scales, and he strongly believes that consciousness it cannot happen if you have a separation of scales such like the ones computers have. And under that premise, he is very strong against thinking that the eyes can be conscious anytime soon because of that architectural property of our computers. So because our computers separate the two things, then the eyes are not conscious. And he thinks that the reason why human brains are related to conscious is because that separation doesn't exist. What else? With the math, I completely agree that I think I said it's true to the degree that that makes sense. And when I said that, thinking exactly on the point that you said, that math is a language, is more about self-consistency and it's not about truth or not truth. I'm forgetting something. Is there any point I'm missing?
No, I think you've essentially covered what I asked there. Just going back to Anil Seth, I mean, I would agree entirely that it's most unlikely that AI, artificial intelligence, can derive from a material object just by creating a complicated predictive processing machine. You can feed as much large language data in as you like, but at the end of the day, it can only make conclusions on the basis of the data it has, and therefore it's a predictive processing machine of some complexity. So I think Anil is quite right there. But he hasn't gone as far as to suggest that consciousness is primary or has primacy over the embodied mind and brain. Yeah. He believes that consciousness is a hallucinatory effect that we experience, rather than believing that the lived experience of consciousness is primary and that it is interpreted for the individual ego through the embodied mind. So it's a question of what you consider as primacy. If you agree that consciousness has primacy, then of course science and the investigation of the embodied mind has a lot of useful things to say about how we interpret our lived experience, but it doesn't as yet explain things like creativity, or, to be honest, inaction, where we actually create our experience out of an input beyond perception. So I think that's, you know, something that is inherent in the work that you've already gone through. I might just make one suggestion that if you are going to follow up with this, you can't stop at physics. I think, or even quantum physics. I think you have to go much further to quantum field theory if you want to start thinking about causes for synchronicity, for conceptualization of time and space, rather than a lived experience of an outside world. So you're in the middle of producing excellent and very valuable scientific results, but they are limited by, as you said, the limits that science has set itself. Science only explores the things it's capable of exploring, and on one of your slides, it threw everything else into the category of magical. And that simply is that the area that science does not address, but philosophy, spiritual traditions, contemplative traditions are exploring and are helping science to understand some of its assumptions and limitations, and hopefully both science and the mystical traditions are going forward hand in hand. But thank you for the years of effort that you put in. I mean, I started studying complexity probably around about the same time as you did, and I was very happy with the mathematics of it. But as I continued to explore consciousness and came to realize that its primacy and jettison basically the materialistic view of the brain from the 1990s, I began to see that we have huge fields to open up, but we have to keep our minds open. We have to continually remind ourselves of our assumptions. So thank you for your talk.
Thank you. No, I completely agree. I very much resonate with the. So one thing that I'm very interested, I really don't like the choice between science and philosophy, for example, or science and art. You have to choose. Are you here or are you there? And part of my interest in exploring the possibility of a non-reductionist science is to what degree you can expand it. But that expansion, I would not like it to be like a colonization, so to speak. It's more like, like to combine things in a harmonious way. And I mean, I know it's challenging. I'm aware of the challenges of that endeavor, but I'm very interested to see where it can go.
Well, if you're actually going to combine them rather than allow science to expand the restraints that it's placed on itself. I mean, but basically, I mean, Boyle started science, and he said that he based this on, I think his phrase was, I can see further because I sit on the shoulders of giants. And of course, the giant he was talking about was Descartes, René Descartes. That was who he was referring to, who said, cogito ergo sum. I think, therefore I am, but actually probably put it the wrong way round. We now have come through the work of the existentialists who say, I am, therefore I think. So if your basic foundation is the thinking mind creates the being, the doing of the mind creates the being, that is at odds with the existentialist and probably the enactive view, which is the being creates the doing. It's an interesting point, but you know, if you can't persuade science to jettison its views, then you basically have to take it down to quantum field theory and say, look, science should be based on this, and it's got much more possibilities for a much broader range of understanding. And maybe the scientists will accept that, although it won't provide very much in the way of grants to create AI computers.
Thank you. Thank you so much, Bruce, for all of this, taking us through these thoughts and drawing out Fernando. And thanks, Fernando, for your responses, and I'm wondering if there are other questions still waiting in the wings, as it were. Please don't be shy if you have a question or a comment. Feel free. Maybe while we're waiting, this doesn't really relate to what was said before, but Bruce's mention of creativity and, you know, this sort of other areas where we are tuned into meaning and meaning making. And I'm just wondering what, this is not your area of research at all, but what, is there any kind of conversation going on around language and emergence in language? I'm thinking the way this question came to me was really thinking about how inaction itself and autopoiesis and autopoietic theory has really been stretched and scaled up, as it were. I guess you could say it that way, scaled up or scaled out to um, the really linguistic bodies and linguistic interactions as forms of sense making, but moving through these different levels. So you talked about scales, moving through the sensory motor, moving through cognition. And so I'm just wondering, is there any sort of conversation going on around that?
Mm. Yeah, I don't have too much to say about language, but two things that occupy my mind quite a bit is about meaning in some specific ways and autopoiesis.
Mm.
In the sense that I think there is a discussion to be have on causation, that I feel there's so much confusion about causality. And like when people say everything is because of the Big Bang, and then the Big Bang is the cause of everything, like I think that's so wrong in so many ways. And I think there is a way to rigorously prove, or I don't know how to express this, but to say that big things do have causal power that is unique for them. And in that sense, big things like us do make a difference, and that's not a way of talking. And so I think there is an argument to be made there. And that sort of connects with autopoiesis in a specific way, because what we were talking before about this interaction of scales, and um, if this argument that if there is a separation of scales in the brain, then it couldn't be conscious because consciousness requires this connection between scales. I think there is something about autopoiesis there, because the way I understand autopoiesis is that what you do makes what you are. So that, and then the function affects the structure. So there is a direct connection between function and structure that is what is broken specifically in computers. Because the idea in a computer is that what the computer does is not what is built for. You know, you can have these different computers built in different ways, but they are all running the same algorithms because they are made such that the function is decoupled from the structure. But when you have autopoiesis, the cell still keeps being the cell because what it's doing to preserve itself. And then you have this link, and so I think that autopoiesis might be in direct antagonism with the second type of emergence.
Mm.
And that has to do with the causality that you have in the macro level that is making a difference for the micro level, and then you have downward causation and all things like this. So I think there is a connection there. And the other sort of hunch I have is that this second type of emergence is actually completely against, sort of opposite to consciousness, but it's very related with cognition, in
Uh-huh.
the sense that I think the second type of emergence is about simplifying details and keeping things that are self-contained, and that's the current way I'm thinking about abstractions.
Mhm.
So, and cognition is a lot about that. So maybe, and maybe that can help. So I have always sort of suspected, I'm in the camp that things, consciousness and cognition are quite orthogonal.
Mhm.
So there are, you can have something very conscious that is very non-cognitive and vice versa. And there are a lot of people that think they are very aligned, and that sort of consciousness is the icing in the cake of cognition. But I don't know, I tend to feel that they are actually orthogonal. And if this way of thinking that maybe this type of emergence is for cognition and not unconsciousness, and maybe the type of emergence that allows for downward causation is more for consciousness and not for cognition, maybe that could give some way to start reasoning about this in ways that could be experimentally validated, and that would be I would find very interesting. So that those are all things that are in my brain now, and I'm planning to explore in the future.
Mm. Yeah, okay, thank you. Yeah, that's actually clarifying in some sense. So I see, maybe before we circle back to you, Bruce, I see Nathan, he has his hand up. Maybe you can ask your question. Unmute yourself, Nathan.
Yeah, thanks so much. And thanks so much, Fernando. This is amazing work and also amazing to get to have this conversation here in this space. My question is more of like a clarification one, though. So somewhere around like on your early slides talking about ontological versus epistemological forms of emergence, and then you're positioning compatibilist emergence kind of between those two extremes of magical and sort of purely reductive. But I kind of missed exactly, are you trying to position this as an ontological form of emergence? Or are you rejecting the sort of the way this debate and you know these things have been described so far? So yeah, we're just hoping for a little clarity on that. Thanks.
Thank you. That's a great question. So I I sort of dislike most of the distinctions, like the strong versus weak. I don't find it particularly useful, and also the ontological and epistemologic. I don't find particularly useful because
Mm-hmm.
uh, I mean this is for the way I think of things. Because I feel that on the one hand, everything is epistemic in some way because always it's from one perspective of someone. But at the same time, the fact that for you, some systems look like having separation of scales, for example, and other systems don't, I think there is a reason for that. So it's not entirely epistemic, you know,
Mm.
and then putting all the weight in the eye of the beholder, I think is sort of avoiding the question that is interesting. That is, okay, I see that, but why do I see that? So in that sense, the distinction I find it a bit unhelpful because I feel everything that is interesting is happening somewhere in between.
Mm-hmm.
And that's why I don't think too much about this ontological versus epistemological emergence.
Great.
Yeah.
Thanks.
Thanks, Nathan. God, also Father Francis, I just want to make sure we get people who haven't spoken yet to the fore here. So Father Francis, and then we'll come to you, Bruce.
Yeah, a lot of the thinking here is very new to me and very stimulating. But I was wondering whether, right, what body of empirical data gives rise to the kind of modeling that you presented? In other words, it does seem that your team is working on interpreting a body of data with which I am not familiar with. You know, and then secondly, of course, whether, I mean, really for, I think our interest in consciousness, but even in biology, is the modeling applicable to living systems?
Mhm. So I would not say this work comes from a body of data. It comes more from a body of philosophy and theory. And what we have been trying to do is to take those ideas and try to make them useful for experimental analysis of experimental data. And then you can take existing data and use these tools to analyze it. So, for example, this data set I mentioned about patients with brain disorders or things like that, that existed, and we can apply these tools and see what happens. Or you can start proposing new experiments that can be more specific to test some of these ideas. But I would say most of the motivation came from previous theoretical work going in these directions. And then what we have been doing is try to spin it in directions that feel it could make this theory more empirically practical. And yes, so another interest was to make a framework that was as general as possible so that it can be applied to basically anything, which is a strength and a weakness because in principle, you can have any data set and you can use these techniques and see what happens. Now, actually, in the early days, I was very adamant of this sort of data-driven stuff. So let's the data speak and etc. Now, with time, I have become more aware that every data has so many implicit assumptions, and Data is always, in my view, a perspective. So the person that took the data was looking from things from certain way and decided to measure this and not to that. And in a way, when we come to the data, we interpret in a way that we think is aligned to the person that took it, but who knows? So data is always capturing a perspective, I believe, in a way that is often not acknowledged. So all of this is sort of very data centered, which is a strength in the sense that you can apply to any data. At the same time, it's a bit of a weakness in the sense that the conclusions so that you can throw the data in, you get numbers, and then you can get statistics and some p-values and whatever, but the conclusions that you can get out of it depends a lot on the data and your beliefs about the data. For example, let's say you have electrophysiology. So you have a number of sensors in your brain and you get data from this sensor, this EEG, and then you do some analysis and then you get, oh, there is this emergent property of the electrodes. And that means there is some center of mass having its own ability to predict itself. And it's like, oh, I'm excited because I get emergence out of the brain. But maybe, just maybe, what you're measuring is activity in the surface, and maybe what you're getting is the source that actually generate the whole data. So it's not emergent, you are undoing the capturing thing and getting what is generating the data, but so depending on the setting and depending on what are the data sources and what are the parts of the system, you might or not might be able to draw conclusions. Maybe your conclusions are not going to be very meaningful because the data on which you use it is you're mostly talking about artifacts of your measurement process. So in that sense, it's not a weakness, but you have to be very careful on the conclusions that you can get out of this because it depends so much on the data that you use. But I take that as a strength. I like something that is very applicable. You can apply it to many cases. Now you have to be very super careful in order to make conclusions. But I think that's good, and that's part of the process of being aware of your own assumptions, as we discussed before.
Yeah, this is a very important problem when you're looking at the data of actual experiments, and you see not only how the charts were designed to express the data that was that turned up, but also then you get back to a critique of the design of the experiment itself.
Exactly.
And I think, all right, so that now I understand where you're going and what the critical approach here is. Okay, thank you.
Thank you, Father Francis. All right, I think we'll end with your question, Bruce. You'll be the last question for this evening. Just got a few more minutes, so if you want to wrap us up.
Yeah, thanks very much. I put my hand up actually in response to the comments on causality that you raised, Diana. And interestingly, it has. I wanted to point out that causality, of course, is an assumption that not only underlies the experiments but also underlies the data. And I think we've come full circle to realize that if you want to broaden beyond causality into our non-linear experiences, which we undoubtedly, non-linear lived experience, which we certainly have, perhaps the most interesting of which is synchronicity, then I think you have to look further afield, as I mentioned earlier, into the area of quantum field theory, or its parallel in Buddhism, Indra's net. So, I mean, there is a philosophical basis for expanding science. And I used the example earlier on. Sorry, I used the experience earlier on of Boyle and Descartes, but there is quite a well-known saying, and I'll finish with that, that everything in science happens twice, first in philosophy and then in science.
Let me make a little comment about the synchrony thing that I feel is interesting. So I love synchrony, as any musician can love synchrony, but at the same time, one of the things that I have found in my work is this idea of synergy that is a little bit different from synchrony in interesting ways, because you could think that synchrony is redundancy in a way. You have a lot of things and they all agree and they are all in sync. And to some degree that's great, but to some degree that's constraining because everybody's in sync. And synergy is a bit different in the sense that everybody's not in sync, but they're connected in a sort of a more loose way. And I find the interplay between synchrony and synergy is very interesting because, for example, when you have a multicellular organism, all the cells are, working together, but they are not in sync because they are all doing different things. So, or maybe they are in sync at specific points and in specific ways, but I feel that the whole idea of synergy opened the space of possibilities of synchronizing. Because also, what do we mean with synchrony? Like maybe there is also, maybe synergy is a type of synchrony, but it's slightly different from the standard way of synchrony that we tend to think, where everything is agreeing in the same thing. In this type of, I think we did a little bit of work on synergistic synchronization, but we never finished it. But the idea would be something like you have oscillators that are not in doing the same at the pairwise level, but at the group level, they are all entangled in the way that the Bach music is entangled at the group level. So yeah, just rambling a bit, but I think there is an interesting dimension that opens there when you start considering also synergy.
Well, synergy is very much based on causality, whereas the usual use of causality is within time and space as a conceptualization that is the basis of the synergy. All I'm saying is that if you take away that assumption and accept synchronicity in the way that it is generally used as a conjunction of lived experience which cannot be explained by time and space, then it becomes more than just synergy. You actually have to look at the assumptions in your data
Sorry, synergy is not related with causality. Synergy is about, let's say you have three things.
Sorry, yeah, no, sorry, I put it the wrong way around. You conceptualize it outside. I'm saying that synergy is probably still based on time and space causality, or the conclusions drawn about synergy are based on that. An explanation for synchronicity in the way that is normally used as lived experience, which can't be explained by causality, would be an interesting area to explore, to expand yours and science's exploration.
Mm-hmm.
Okay, well, thank you. And Fernando, I want to leave you the last word. We're going to wrap up in just a minute or so, but a huge thanks from us. And would you like to just add anything else or say anything else before we wrap up?
Just thank you. Like it was very, very, very happy to be here talking about all these subjects that I'm really passionate about. And yeah, thank you for the invitation.
Thank you. Thank you so much from all of us at MLE and the whole team here, and Gabor as well, who's part of our team as well. So I think we have an end slide with some announcements. There we go. So for anyone who'd like to keep following our online programming, you're very welcome to take a look at our website. You can find upcoming events there. We'll be sending out a newsletter very soon. But we will actually have the next MLE Friends talk, which is not on the slide, but which I'd like to mention, from another researcher who is former faculty at the Esri, Inara Garcia, who is working really in participatory sense-making, precisely coming from this tradition of the enactive approach. And so she'll be giving a talk on December 11th. So it'll be a Thursday again, same time. Look for a link in your inbox. So those who are interested in joining us, you're very welcome. And then we have a number of different events open to the general public in December. So we have a practice session on the 16th. We'll have a very special arts and enaction event with Dutch artist Lorraine Weyers on the 17th of December. So we'll be sending more information about that, a very exciting event. And we'll be dropping our next episode of the podcast on December 18th. And for those who have also maybe heard of the upcoming Barcelona Conference on Power and Care next May 2026, the deadline is this Sunday to get in talk proposals and poster proposals. And so if you're interested in coming to present a talk or a poster, be sure to fill out the application by then. And general attendees can sign up and apply at any time in a rolling basis. So that's enough from us on our side. Thank you everyone for joining, and also those who are listening down the road on the YouTube channel. And of course to you first and foremost, Fernando, for this really, really stimulating talk. And we look forward to following your research down the road.
Thank you.
Thank you. Thanks everyone. Take care. Have a good day, good evening, wherever you are.